Dude, and it sucks when you're wearing your gloves trying to use the mouse pad.
God, it was so infuriating.
And then we had an error come up like 5 times.
Oh, you're joking.
Yeah, so
We had.
it wasn't because of our absorbance, Emma.
Yeah,
It was because of the program for the error, okay?
I'm just
The
crying.
absorbance.
I'm crying because he's like, oh no.
You guys know that.
Oh no.
It's because I told you errors.
I know.
In lab before now.
That's true. We can talk about it. You know.
Discussion.
An error, even though, what's her name? It's even like, make sure we bring the result of an error.
Just the program is just old. It's so old. It's like early 2000s right there.
Oh, it's just.
Cool though.
It's just a Chromebook.
Cool. It's like a little guy.
Yes. That's not a problem.
So are we doing projects?
Sure.
We didn't even vote yet, and you're just like, I'm changing my mind.
You were supposed to vote.
I already voted. Yeah, I thought we were all voting in class. I didn't know we were voting.
Are we voting in class? Oh, 1, 2, 3, 4, 5, 6, 7.
We were doing.
Who is for the project?
Yeah.
We'll do the. You could vote for each other.
Your hand.
No pressure. Okay, your votes are recorded. Who is for the exam?
This is your opportunity.
Yes. Okay, so I was talking to lobbyists of the exam that there is a wish. I don't know what. Not thank you. Wish. There is a wish to learn more and practice more in problems, right? And probably it is a major motivation rather than risk your grade by dropping 25 points of the overall 25% of the whole grade by not doing exam in the limited time, right? You just want to practice things.
Yeah.
So as a minimum, I can consider those most of the practice exam problems during the remaining classes, and then you'll get what you want. Right?
Okay.
So you'll get just some training. Because if we do exam as it should be, without benefit of the doubt, on a stopwatch, it is a big challenge. And I just imagine myself on your place. I do not want to have this big risk. Because when you do projects, it's maybe comparable time to what you spend in practicing problems on your own. Because doing only homework is not sufficient to successfully pass an exam. It would mean that you sit every day 2 hours and practice on stopwatch to do not only correctly but in a limited time. Which I admire that there are so brave people who are interested in this. But it is more like a sport rather than science. Maybe in the future you need to pass subject GRE for graduate school, and then it would be a good preparation for those who are supporting exam. But those who are not going to most ambitious schools would never need to pass subject GRE. It is just a torture. So agreed? No, good. It was I'm celebrating unlimited joy because I like projects more myself. I checked the web form this morning twice, and just 15 minutes before class, I saw additional votes for the projects. When I was preparing for the class, it was too late to modify, but here is your things. If you didn't vote online, you can just record projects. And about the subjects of the mini research projects. If you ever redecide, it's fine. You can redecide until you submit your written report and which is enough time. But I need your votes as soon as possible right now, so that I modify my narration during the labs, so that I fine tune. And if no one selects NMR, I'll just skip it. If there's several NMR enthusiasts, I will put an accent on it and stuff like this, because one cannot embrace everything. I noticed your vote, I noticed Emma's vote, but you can either repeat or let it go. And what are we going to do in today's class? The academic didactic part will be, today is the last day of harmonic oscillator. We will say goodbye to harmonic oscillator today. And we do need to go the same path as we did for other simple models. One of the very conceptually important concepts, repeating words, is Heisenberg equation of motion and Ehrenfest theory. Do you remember more or less this? So when we were in free space, we saw that one can predict average position of the wave packet just by solving a couple of differential equations for expectation values. And they were matching what we have for classical first law of Newton. Things move with constant velocity. The same, I mean, not constant velocity, but the same ideal agreement between quantum predictions and classical predictions are available for harmonic oscillation. Well, I would like to go over the details and provide a proof, but it is an amazing situation. It's not so comfortable in other systems, but we need to use benefit of this situation. Basically, if and homework, whatever number, extra credit with 40 points where you solved oscillating differential equation for oscillating solution. We're going to get same type of there are exotic subjects on the backside. If you want something really exotic, or you already made your decision.
I don't know yet. I want to talk to you.
Okay, we'll look at the very last. No, I didn't put it here. I will return to the subject. Okay, give it to me. I will just touch the strategy of the didactic subjects. Then I will quickly return to projects. I will read through and give some comments, and then we'll go to derivations. And depending on your mood and my mood, I may practice old-fashioned or just short slides, and depending on time allowance. So the Heisenberg equation of motion for harmonic oscillator. The center of the wave packet oscillates for force and back, like a sine function. If you momentum, we will do a sine function. They will be out of phase. And if we draw expectation value of position and expectation of momentum of FALL2023, we were voting about exam versus projects. The majority vote went for the projects. And I know that you already put your vote, which project you would be interested in, right? Okay, just inform you. Yeah. So if one does set coordinates of position and momentum for classical oscillator, if you consider interatomic bond just as a classical variable, so we have a mass on a spring, then with time momentum increases, position decreases, and it will go on circles, right? Phase diagram of oscillations. And if you do coupled ODE with the solution, the only thing is to prove that we will get the same thing if we practice expectation value for position momentum. We are going to use a concept of creation and annihilation operators. And it is very appetizing. It is very tempting. It is very pleasant to solve equations not for x and p, but for a and a dagger over time. So we are going to solve these equations and then reconstruct position and momentum and see that the solution will give this diagram. And then one can pump the cheeks and tell in presence of general events. The correspondence principle in limiting cases, quantum reproduces classic. Right? But we're going to see it in technical details, how it goes. Okay, now quickly returning to the projects. Okay, so let me. Yeah, I'll probably do things on the board and then show slides. Otherwise, going forwards and backwards will be too much. So one of the class attendees did select an interesting subject of photocatalysis. So I'm going to tell a couple of words of what is going on and how to start thinking about it. So, did anyone put wires from the battery, car battery, into water? Who is lost?
Is that a research topic, or are you asking if we've done that before?
I'm asking if you've done it before.
No. Is that a research topic?
Yes, yes. So what happens if you put biased voltage electrodes into water or salt water?
With enough voltage, you might produce a smidge bit of hydrogen gas.
Okay, on one electrode, on the one with negative charge. What is going on the one with positive charge?
Oxygen, right?
Yes, yes. Oxygen is more complicated. So whoever selected electrode is on hydrogen, it is twice as similar, because for hydrogen one needs 2 electrons, for oxygen one needs 4. So it's more complicated. So if we do have a metal electrode, and then it could be anything that gives a bias with abundance of electrons. And then in the water, H minus, H plus, right? They are moving freely, and if it is a metal, they may absorb just to the surface. Okay? And it is balanced by counter ions in the solvent. But in case we do have negative charge on the electrode, there is a chance that this electrode will go into protons, reduce them to neutral charge, and then so positively charged protons have same charge and they experience Coulombic repulsion. They may absorb and get attracted to the metal surface, right? But they do not like each other. But as soon as we neutralize them, they start attracting each other, forming this bonding orbital. And then at the next time stage, they just form a bond and the molecular hydrogen departs, right? So how can one apply stuff of simple model that we did in the class and in the lab to this problem? One may want to establish, we cannot go to too many coordinates. Like 1 or 2 is maximum what we can do as of today. But we can set up the distance between hydrogens as x and distance from their center of mass to the surface as y, right? And then identify a potential energy surface, like how the total energy depends on these 2 parameters and on the total charge of the electrode. Then, depending on the charge, it will be either completely repulsive, they will repel each other and never connect. It could be attractive, more or less attractive to the surface, and it could be a preferable potential that facilitates departure of the molecular hydrogen. Okay, I will do additional illustration when we go to slides. I have prepared a slide and we'll discuss it. Matter of interaction by 2. There are polarons. By 2 matter interaction. Yeah, that will be fine. So, overcoming a reaction barrier for certain compound, maybe to decompose, can be too challenging for thermal chemistry. But if one assumes existence of the excited state potential energy surfaces, it could be much simpler to photoexcite, and then the system will travel along excited state potential energy surface and overcome the critical distance that corresponds to intact molecule. And then one can de-excite and get to the from reactant to the product much easier than through thermal activation. So this is general paradigm for light-to-matter interaction, and there is not exactly direct Marcus theory, but there will be part of in the remaining time of our exercise when we will consider in class we will consider just harmonic oscillators of different equilibrium position, and for the projects for the lab we can consider more exotic surfaces. So this situation of offset potential energy surfaces was awarded by Nobel Prize to Rudy Marcus for electron transfer theory, and it is a very general paradigm to combine different electronic states and nuclear degree of freedom. So Marcus theory is something sufficiently novel and sufficiently simple. Well, you already made choices, but okay, feel free to you decide. Okay. Laser and NMR. They're very similar. So this is what we will be doing on second last lecture before end of the class. Who heard about NMR? Good. So there is a magnetization, right? That is more transversal magnetization that changes over time. So the nuclear spins have components along Z and across Z, across magnetic field, and there are so many of them. To measure something, they need to come in the same phase. So this is the easiest way to think about it, that there are 3 components of magnetization, Mz, Mx, and My. And this is like a globe, and each individual spins are like runners that reside on equator. And when they come to the same point, then the magnetization adds together and gives the biggest signal. So to reproduce an NMR signal, one needs to have several spins added together. And then one can get the magnetization over time. If one wants a laser, then two-level systems are the same as nuclear spins mathematically. And if they are coupled to harmonic oscillator for electromagnetic field, when they come into phase, they dump all energy into oscillator, and we see a spike in the pulse emission. It is one of the subjects that I probably would like to do if I have time. And so these are done. I noticed that some of you are interested in differential equations, and some of you can be led by hype of machine learning. There is a research that a postdoc in my group is doing for looking how the quantum dots are losing their energy over time, so quantum relaxation in electronic states. And there is an attempt to predict this behavior, not by solving equations in a fair way, but by mimicking it through machine learning. So then there are simple codes to do it. I just wanted to show all. Okay, so it's about time to go to our main subject. So here is my vision of what we can do in the remainder of the semester. So we are saying goodbye to harmonic oscillator. Then we need about 3 lectures for rotator and hydrogen atom. Another lecture for very detailed review of Bohr model. It's not modern, but it is a foundation if you ever need to teach. So it's a solid foundation. You'll enjoy. There will be movies and fun and maybe some demonstrations. Do we have Wednesday as a work day next week? No. So everyone departs. We don't have lab, we don't have lecture, we have only Monday, right? You're sure?
Yeah, Thanksgiving.
So Thanksgiving weekend starts on Wednesday.
Yeah,
No one is here on Wednesday.
Students are off campus Wednesday, offices are open, but past that.
We should be here Wednesday.
We
shouldn't be here Wednesday if we are not.
Relaxation and being off campus is good. Okay, what else? About this time, I will invest the whole lecture on instructing what to put into the reports. So the projects are mini projects. They can be completed in a short time. And the main challenge is not to do actual work, but how to report them. And I will discuss it in fine details. Then we'll have a weekend to implement the suggestions, and we will do have a similar of collecting grading. You'll read works of each other. And then after this, authors will have a chance to refine their works. Okay. So spin NMR for induction decay, what I briefly covered, and molecular spectroscopy. So here it would be a problem that some of you attempted to solve for population of orbitals for going between ground and excited state, seeing the populations in the excited state. It was one of the problems in the practice exam, so we'll cover it during the class, for sure. Then in here, I hope there will be time to cover the very last problem for the practice exam about interacting spins. And here if will be problem whatever 2 or 3 from practice exam on reconstructing parameters of nitrogen oxide molecule from rotational vibrational spectrum. So as a minimum to satisfy your drive to knowledge, we'll consider this heavy problems in class with all the details. And maybe there will be more, well, you already showed you are so strong in commutating operators. Lack of time gives adrenaline. So here is something that one of the students in similar, well, not in similar, in computational chemistry class, which is offered as elective next semester, did a few years ago. And this movie illustrates this oversimplified small model for proton reduction. So those bigger spheres are metal, so platinum in this case. The surface of this little metal cluster is fully saturated with protons, and and there is a little negative charge. So as time passes by, you see that there is a development of molecular hydrogen here, and it departs from the cluster. One few, but one can convert the positions of ions and total energies along this trajectory and extract potential to do things related to what we do in class. Thank you for doing this. So we'll have rotator and spin, and now we are going to get this thing as an answer of today's meeting. Anyone interested in getting an extra credit or getting an immediate increase in self-esteem? Please go ahead and correct errors you see in this slide.
There is not an M next to the, or there's not a M next to the cosine. The top part, right? So the cosine on the top left, why isn't there an M there?
Or there's no negative sign.
Well,
But it's like,
cosine, all dimensions are here for the cosine. So it's okay. I would be mostly supportive for this cosine having no mass and no frequency. What about the image?
I was gonna say, is there supposed to be like a negative at all in any of the cosines, or are they both positive just generally?
We'll figure it out at the end of the meeting. But if initial condition is absence of momentum and only the elongation in respect to equilibrium, right? Then this terms
they should be spinning the other way, right?
yes, J plus 1. I was waiting for this one. Let's applaud to James. Everyone understands, right? So when we accelerate, momentum increases and position decreases. Okay. When we practice our fluids in the lab, we are doing correct and general procedure of finding wave function at each point of time, and then moving forward to evaluating the expectation value of observer, right? Making quantum sandwich. For some problems, one can get the same result by cheaper effort. And sometimes one can avoid the wave function and just write an equation of motion for expectation value, which is Heisenberg equation of motion if it is relates to any operator, and people call it Heisenberg Ehrenfest theorem when it deals with position and moment. Okay. So on one hand, on another hand, you have completed not the practice exam, but last homework before, where you were successfully commutating harmonic oscillator ladder operators with Hamiltonian, right? We are going to take benefit of this little practice, and sure we did this because you guys did it in your homework, right? But the combination of creation and integration operators, if we redo it as product of independent operators in Dirac notation, will give a projection with index of the eigenstate in front, right? We try to swap the order of operators. Then you get the same projection, but just by following this rule of snake and mouse, you'll get that there is +1 in front. And if we subtract the anti-normal and normal order of these operators, you'll get just an identity operators with ones along the main diagonal. So now it means that if we practice commutator with equation and annihilation, it will be normal minus anti-normal will be -1. If you do annihilation and creation, it will be anti-normal minus normal will be +1. And this relation allows to do a substitution when we need it. So the anti-normal ordering can be always replaced to normal +1. You do not need to be very careful and attentive because you already did it. You're just reciting it for just in case. So we may set up the following plan. Since position and momentum, which are declared interest for this meeting, are expressed in terms of creation and annihilation as a linear combination, we may find trajectories, expectation values of position of creation and annihilation operators, and then combine them as the linear combination back to reconstruct position and momentum. Why we need to go the seemingly longer path? Because if we try to compute position and momentum with Hamiltonian, it's also doable, but it will be a couple of lines longer and less elegant on one hand. On another hand, if we plan to have a meeting on spins and NMR before the end of semester, we will see that there are creation and annihilation operators of the spin, for the spin up and spin down, like raising, swapping spin down to spin up, lowering, swapping spin up to spin down. And after doing this little exercise today, we will establish a foundation to see a lot of similarities between ladder operators for harmonic oscillator and for spin. If we go immediately into expectation values for position and momentum, we can do it. Basically, you do not need me. You can go to the blackboard and derive it. It's not too complicated. But then we miss this foundation for analogy. What are we going to get in the next few minutes? That the expectation value of an initiation operator and an eigenvalue of an initiation operator, I just noticed, they both are time dependent and they accumulate phase in a complex phase. In a complex phase. If you look for expectation value of either initiation or operation operator, they will be just conjugated and they will accumulate phase forwards and backwards. So this property is very easy to derive. On one hand, on another, when we go to spins and introduce their operators, they will have the same property. So expectation value of operator will accumulate phase forwards and backwards in a complex plane, and this will be a major foundation for NMR signal. So it's maybe this course is not the best in the field. There are some other instructors and courses with maybe slightly different accents, but here it is material is connected. So it's a laying foundation to think about NMR in the future. I was just curious because someone has a fan going on. Probably it was either very intense computation or updates. So we do Heisenberg equation of motion. We do have a Hamiltonian which is normal ordered creation and annihilation plus 0-point energy and frequency in front. Now we are reproducing what you did in your homework, whatever, 7, right? So we compute Hamiltonian and annihilation operator, which the factor 1/2 goes away because it will be cancelled anyway. And then we do open this thing as a normal order A dagger AA minus A dagger A. So we identify that there is a abnormal order for one fragment or one factor in this line, right? And where we see abnormal order, we replace it according to the what we discussed before, the commutation between equation and annihilation. So we replace abnormal order to normal order plus 1. And then it means we swap these two operators, and then we have minus 1A, which is inherited from this little a. Then first and second term, which are both normal order and have 1 A dagger, 2 A without dagger, they cancel. And then the only remaining thing is minus annihilation operator. So we get that commutation between Hamiltonian and annihilation is minus A. When we do the same thing for creation, we get, well, and we need to keep H bar on, right? When we do this commutation with creation operator, we get this same operator again, and plus sign and the factor. So what is interesting and somewhat pleasant, there's a chance that no one of us will ever practice Heisenberg equation of motion again in the, maybe once again for spins and then maybe not again. But those who try to do it through the career, typically run into difficulties and challenges, so that you want to practice this similarly with integration. You compute your operator of interest with Hamiltonian, hoping that it will be closed differential equation. Then you take another operator on the right side, try to commute it with Hamiltonian, and then you get a third operator, and then you get a chain of operators. Sometimes you get a product of operators nonlinear, and they are hard to solve when one just arrives to a system of nonlinear equations, multiple nonlinear differential equations which are connected to each other. In this pleasant situation, one has the simplest possible commutation. So commuting operator with Hamiltonian reproduces operator itself, right? So it means we will have self-contained one differential equation for A and self-contained one differential equation for A dagger. This is a big, which you cannot expect all the time. Okay. Now, what do we do if we need to solve this equation? Well, it's a little, because of my lack of time and adrenaline, we don't have too much time, but probably in next years, this simple problem should be done by some of the classmates on the board, because it's so simple.
It's just inseparable, right?
Yes. So with or without this sandwich, one can solve this differential equation, right? And another thing that I was surprised at my undergraduate times, one can write down and solve equations not only for observables, which are functions, also for operator. So symbolically, algebraically, it is possible, and no one would criticize a person who solves it. So if one divides both left and right by A and multiplies by dt, we have everything related to A at the left, everything related to time at the right, integrate left and right, and put solution into the power of solution of this integral will be natural, right? This will be just t, and then we put solution into the power of exponential, right? Then exponential of log will be the function itself, right? And then we have the annihilation operator for time t will be annihilation operator at time 0 for initial condition oscillating minus I omega t. So in sometimes complicated subject of physical chemistry and quantum chemistry, there are some sweet spots which are easily solvable. So if one reproduces this stuff for a dagger, guess what would happen with the sign? Huh?
Positive.
Yes, it will just accumulate phase in the opposite direction. And it is very interesting that this expectation value of annihilation operator agrees with eigenvalue of annihilation operator, right? It accumulates phase in the same way. It is an interesting observation in this situation. Okay, so for a dagger, it is accumulation of phase in the opposite direction. Now we need to add and subtract them together to reproduce position and momentum. There is a very unpleasant stuff that I hate to match the constants up front, and there is as typical in solving differential equations, one needs to match initial conditions. So if maybe I'm lucky that I do not need to do it because of the pressure of time, but if we need to do it in all details, the initial conditions are obtained for creation and annihilation operators at time 0 by setting up this connection and making a quality of this linear combination and initial values at time zero. And then one would get a system of linear equations and reproduce what are the initial conditions. This is all doable, but a little exhausting. It's additional, maybe 10 minutes. In case we start with only bond elongation, then there will be equal parts, they will compensate each other, and it will be ideal situation. But for general initial condition, any point on phase space, there will be okay, reproduce here the general terms. Yes. So if we plug in the initial values for position and momentum, then here is how so one is having the rotation operator as function of time and annihilation operator as function of time. They both add together and contribute to position as function of time. They both oscillate. But now we need to go back into expressing annihilation and creation operator as function of position and momentum at time zero. And if we do it carefully, then there will be so total 4 terms, and we can group them. The terms that corresponds to position in both groups will go here, and because of this combination, we will have adding together both forwards and backwards oscillating parts, and for part that corresponds to momentum, we will regroup them into here, and there will be opposite sign. So each of groups will be weighted by initial value of position and momentum, and by Euler equation, first term will just give cosine, and second term will give sine. So if we start not at the simple elongation, if we elongation and kick, then it will be phase offset, right? So you just start away from the maximal x on the phase diagram. Sine. By taking care of all constants, one can get the initial value of position, initial value of momentum that contribute to the answer for position. The same trick can be done for the momentum, and then one can express the final solution to time-dependent position and momentum as the time-dependent linear combination of initial conditions for position and momentum. So if we do not have if initial momentum is 0, then it is the cosine and sine, right? If there is 0, sometimes let's say 1. But if there is both, if there is a kick, non-zero momentum, then it is a little longer expression, right? So there is a sinusoidal component for position over time. I hope to see a yellow slide telling that that's it. Oh, okay. And extra credit to James for opposite direction of rotation. They were symbolizing many, but looking forward to see you this evening.